Hello and welcome to our lesson on rational inequalities. This is going to be from section 8.6 in our text, and we're going to cover a little bit of introductory stuff before we jump into the examples. So, what I've tried to do here is boil it down to three main steps that are involved in solving a rational inequality. It's going to be a little more involved than just the three steps, but I think this should cover the majority of it. The first step you need to do is you need to make one side zero. So since we're talking about an inequality, that means that we're going to have either a less than or equal to, or a greater than or equal to. What you need to do is make one of the sides of the inequality zero if it's not already zero. I prefer the right-hand side to be zero, but that's up to you. It doesn't really matter. Step number 2, find the critical points. Once you get one side zero, in order to find the critical points, you need to set the numerator and the denominator equal to zero and solve. So provided that the numerator and the denominator both have variables, you're going to get critical points from the top and the bottom. And then what you'll do is you'll put those on a number line with open or solid dots. And then the third step, we're going to use test points to determine the intervals of the solution. And so that's basically it. But to really get a firm grasp of what's going on, we need to look at some examples. Our first example we're going to look at is number 55. If we refer to the steps, remember I said the first step is to make one side zero. Notice that the right-hand side is already zero, so that's step number 1 accomplished. Step number 2 is we need to find the critical points. Now, since the numerator does not have a variable, it's not going to produce any critical points. So only the denominator needs to be set equal to zero and solve. This is how you find the critical points. So we're going to move the plus 5 over, which is going to make that minus 5. Divide both sides by 2. And we get our first, and in this case, only critical point of negative 5 halves. Now you can express that as negative 2.5 if you want, or negative 2.5, but I like it improper. So this is going to be my critical point. Then the next step is to go to the number line with our critical points. And the critical points on the number line are going to have either an open circle or a solid dot based on where they came from and the inequality. Okay, so listen close. If your critical point came from the denominator, it will always have an open circle. It can never be a solid dot if the critical point came from the denominator. If you have a critical point from the numerator, the inequality will determine whether it's an open circle or a solid dot. So in this case, we don't have any critical points from the numerator. So we'll talk about whether it's open or solid in the next example. Now, for the third step, once we get our number line with our critical points, the next thing we need to do is pick test points. You need to pick a test point in each interval. So here we have only 2 intervals. The test points can be any number that you want to pick, provided that it's in that region. So I need a number less than negative 2.5. I'm going to go with negative 5. It can be anything in that region. You could have picked negative 10, negative 100. It doesn't matter as long as it's less than negative 2.5. And then I need a number on the other side of negative 2.5. I need a test point greater than negative 2.5. I'm going to go with 0. Anytime that you can pick 0 as a test point, do that, because 0 is an easy test point to work with. Now what we need to do is we need to take these test points and we're going to plug them back into the inequality to see if we get a true or a false statement. So first we're going to start with negative 5. Substituting, that's going to give us 2 times negative 5 plus 5 and we want to know, is that fraction less than 0? So 2 times negative 5 is negative 10. Negative 10 plus 5 is negative 5. And negative 4 over negative 5. Negative over a negative makes that a positive. Positive numbers are not less than 0. So this would be a false. And so we're going to label that false up here. Then we're going to test 0. So we're going to plug 0 in. That's going to give us negative 4 over 2 times 0 plus 5. And we want to know, is that fraction less than 0? So these are our two test points being tested. We get negative 4 over 0 plus 5 is 5. That fraction ends up being negative, and negative numbers are less than 0. So that is a true statement. So once you've determined each interval, whether it's true or false, you need to shade the true stuff, because that indicates the solution set. And we're going to express this shaded region in interval notation. So the solution in interval notation is going to be parenthesis, negative 5 halves. Remember, we use a parenthesis since it's an open circle. If it would have been a solid dot, we would have used a bracket. So negative 5 halves, notice that this shaded region goes to infinity. And so that's going to be to infinity, and that is our answer. Now, what I want to do to add to that is I want to show you how you can use Desmos to check these problems. So in Desmos, you're going to notice that I've already input the original problem just the way it looked, and I'm going to turn that graph on. Notice that it indicates the shaded region going to infinity. No matter how much I scroll out, that shaded region goes to infinity. And then what I want to know is, I want to know, where does this shaded region start? Well, according to my answer, it should start at negative 5 halves. And so what I've done here is I've typed in the inequality that represents everything greater than negative 5 halves. If I turn that on, you're going to see that it does overlap the original problem. So this was my solution set. Everything greater than negative 5 halves, not greater than or equal to, strictly greater than, since the original problem had a less than, it didn't have the equal to part. And this indicates that my solution set is correct. Negative 5 halves to infinity. And that's how you can use Desmos to verify your solution set. Our next example, number 57, here we have another rational inequality. Notice that the right-hand side is already 0, so that's step 1 achieved. Step number 2, since the numerator and the denominator both have variables, that means they're both going to produce critical points. So I want to set the numerator equal to 0 and solve, and I want to set the denominator equal to 0 and solve. So first, we're going to divide both sides by 2. X equals 0 is my first critical point. For the other expression, moving the negative 4 over makes it positive 4, and that is my second critical point. Now that takes care of all of the critical points. Once you've got your critical points, you need to go to the number line. I need to plot these critical points. Please make sure you put them in the right order, 0 and then 4. And then I need to determine if they have an open circle or a solid dot. So since the 4 came from the denominator, it has to be an open circle. Critical points that come from the bottom can never be solid dots. They have to be open circles. The 0 critical point came from the numerator, so whether it's open or solid is based on the inequality. Since the inequality has the equal to part, it's going to be a solid dot. And that takes care of the critical points. Now I need test points. We have 3 regions, so I need 3 test points. So first I need a number less than 0. Let's say -5. Remember, you can pick anything that you want as long as it's in that region. I need a number between 0 and 4. Let's say 2. And then a number greater than 4. Let's say 5. So those would be adequate test points. I then need to take each test point and plug it into the inequality to see if we get a true or a false statement. So starting with -5, we're going to say 2 times -5 over -5 minus 4. And we want to know, is that greater than or equal to 0? Well, 2 times -5 is -10. -5 and -4 is -9. Negative over a negative makes a positive. So is a positive number greater than or equal to 0? Absolutely. And so -5 gives us a true statement. Now, if you want to, you can go ahead and shade that region. Remember that you're going to shade the true regions. Next, we need to test our 2. Our next test point is 2. So plugging that into the expression, 2 minus 4 greater than or equal to 0, we want to know if this is true or false. So 2 times 2 is 4. 2 minus 4, -2. 4 divided by -2, that's going to be a negative number. I don't really care what it is since the right side is 0. I just need to know if it's negative or positive. Negative numbers are definitely not greater than or equal to 0. So that's going to give us a false statement. And then we're going to test our +5. So 2 times 5 over 5 minus 4, is that greater than or equal to 0? Well, 5 times 2 is 10. 5 minus 4 is 1. 10 divided by 1 is 10, which is positive, which is definitely greater than or equal to 0. And that also gives us a true statement, so we can go ahead and shade that region. Now, did you notice that the trues and falses alternated? TFT, and then if you look at the previous example, it was false and then true. So what I want to do here in this example is let you in on a little secret. And the secret is that about 90 to 95% of the time, these will alternate. TFT, FTF, not 100%. It's not always the case, but most of the time, these regions will alternate. Now that I've got the true regions determined, I can write the solution set. So the shaded regions start at -infinity, and the shading goes up to 0 with a solid dot, which indicates a bracket. And since there's a gap in the middle, I need to use the union symbol. Remember, the U is the glue that sticks the two pieces together. And the next region starts at 4 with an open circle, so that means a parenthesis shaded to infinity. And that is the solution set this time. And our next example, number 59, here we have another rational inequality. And what makes this one different than the other two we've done is that the right-hand side is not 0. So step number 1 says to make one side 0. It's definitely going to be easier to make the right side 0 because we just need to bring the 3 over. So what that'll give us x plus 1 over x minus 2 minus 3 greater than or equal to 0. Now, notice at this point that I have 2 terms on the left. What I'm going to have to do is I'm going to have to combine those terms so that I get a single term on the left. And so what we're going to need to do to the 3 is F it up. We're going to need to fraction it up. And remember, to subtract fractions, you need a common denominator. So I'm going to have to find a common denominator for x minus 2 and for 1. Well, it turns out that the 1 needs the x minus 2 and the x minus 2 needs the 1. Remember, if your denominators are different and they're algebraic, you just give each one the other denominator. You can get a common denominator that way. Yeah, okay, I know what you're saying. You're saying, well, if I give it a 1, 1 times anything is the same thing. Did I really need to give it a 1? No, you don't, okay? But the other one, the 1 needs the x minus 2, means the denominator is going to end up being x minus 2. And I know, again, you're thinking, well, wait a second, whatever you do to the bottom, you have to do to the top. Yeah, so we have to multiply the top by x minus 2 also. So what is that going to give me? That's going to give me x plus 1 over x minus 2. Now this minus 3 is going to need to distribute to the x minus 2. So that's going to give me minus 3x plus 6 all over x minus 2. And that's going to turn into addition. Since I included the negative with the 3 to distribute, then the negative's already been taken care of. So that really turns into addition now. And that's going to be greater than or equal to 0. Now, let's combine our fractions. Now that they have a common denominator, we simply add the numerators. X minus 3x gives me a minus 2x. 1 plus 6 gives me a 7 all over x minus 2 greater than or equal to 0. So do you see it's a little bit more involved when one of the sides is not 0? You have to make it 0 and then get a common denominator to get your fractions into a single fraction. That is absolutely necessary. Then you can set the numerator and the denominator equal to 0 to find your critical points. So negative 2x plus 7 equal to 0 and x minus 2 equal to 0. We're going to get 2 critical points. Moving the 7 over makes that a minus 7. Divide both sides by negative 2. Negative over a negative makes a positive. So that's going to be positive 7 halves. Again, you could write that as 3.5 or 3.5, but I like it improper. And negative 2 coming over is going to give us x equal to 2. Those are our critical points. Then to the number line. I've got 2 critical points. Remember, you need to make sure that they go in the right order. And 2 is smaller than 3.5. So it's going to be 2 and then the 7 halves. And then I have to determine whether those are going to have an open circle or a solid dot. So notice the critical point of 2 came from the denominator, and so that has to be an open circle. The critical points that come from the denominator can never be solid dots. The 7 halves came from the numerator, so that's going to be based on the inequality. Since we have the equal to part, that's going to have a solid dot. If it would have been strictly greater than 0, then that would be an open circle. Now that I've got my number line with my critical points, the next thing I need are test points. Remember, you have to have a test point for each region. So my first test point has to be less than 2. I'm going to pick 0. My next test point has to be between 2 and 3.5. I'm going to go with 3. Remember, you can pick any number you want, provided that it is in that region. And then I need a test point bigger than 3.5. I'm going to go with 4. Yeah, no, I'm going to go big. Let's go with 10. Remember, you can pick whatever you want, as long as it's in the region. Now, these test points need to be plugged back into either the original problem, that would be the safe bet, or you can plug them back into this inequality where it's strictly greater than or equal to 0. And I think what I'm going to do is I'm going to plug them back into the one where it says greater than or equal to 0. You do understand if you made a mistake in your scratch work, then plugging your test points into this simplified version is going to be off if you made a mistake, but then so are your critical points going to be off. So it doesn't really matter. All right, so here we go. Plugging in the 0. That's going to give me negative 2 times 0 plus 7 all over 0 minus 2. We want to know, is that greater than or equal to 0? Well, that's going to be 0, which leaves 7 in the numerator. 0 minus 2 is negative 2. Positive over a negative makes a negative. Negative numbers are not greater than or equal to 0. So the 0 gives me a false statement. Next, we're going to check the 3. So that's going to give me negative 2 times 3 plus 7 all over 3 minus 2. Is that greater than or equal to 0? Well, negative 2 times 3 is negative 6. Negative 6 plus 7 is 1. 3 minus 2 is 1. 1 over 1 is 1. And 1 is greater than or equal to 0. That is a true statement. And so we can go ahead and shade that region. And did you hear me say a second ago in the previous example that these intervals will most of the time alternate? So if I've got F and T, this is going to be F since they alternate. But it's not guaranteed to alternate. So I'm going to test the 10 just to be sure. Negative 2 times 10 plus 7 all over 10 minus 2, is that greater than or equal to 0? Well, negative 20 plus 7 is negative 13. 10 minus 2 is 8. Negative over a positive makes a negative. Negative numbers are not greater than or equal to 0. So that is indeed false. Now that I've got the shaded regions determined, I can express the solution in interval notation. So where does the shading start? The shading starts at 2 with an open circle, which indicates a parenthesis. And the shading stops at 7/2 with a solid dot, which indicates a bracket. Now, do you understand what this means? This means that any number in this interval, if I plug it back into the original problem, I will get a true statement. That's what it means to be the solution of a rational inequality. And that's going to do it for this particular lesson. So if you have any questions or comments about anything that I've done so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.